Good morning, Stats. How are we doing today? So we're going to move on to chapter 5, and I think we have a pretty easy start to chapter 5. Just some vocabulary words that we need to understand, and then really a lot of things that we did back in chapter 4 and things that should make sense after doing the probability. So, but again, really important um, vocabulary words here. So we're going to be dealing with two types of random variables. Okay, two types of random variables. And objective one is to verify that the probability distribution of a discrete random variable is valid. So first we have to know what a random variable is. And this takes numerical values that describe the outcomes of a chance process. Again, chance process being random, okay, and then numerical values. So that's what makes it a random variable. So probability distribution of random variables gives the possible values and the corresponding value. So again, the value will be written at the top of the table, and then the probability will be underlying it right as well. So the value for the first value and the probability will be right underneath it. Okay, so this is important. Two things for a probability distribution to be valid. Okay, the probability is pi, and that's just a subscript that we say that this is a valid, must satisfy two requirements. Really important here. Here's the two requirements. And I think you should have seen this before. Every probability is a number between 0 and 1. It's all inclusive. You can't have anything that's less than 0, and you can't have any probability that's greater than 1. And again, these can be written as percentages as well as decimals. And then the sum of the probabilities is 1. When we add up every probability, it has to add up to 1. So that's what will make the probability valid. Again, all stuff that you've heard before back in chapter 4. It's just we're now giving a value. Each value is going to have its own individual probability, and we're able to list them on a table. Okay, so objective one is to verify that the probability distribution of a discrete random variable is valid. So the first thing we have to understand is what is a discrete random variable. Okay, we use a capital letter X to show that it's a discrete random variable. It takes a fixed set of possible values with gaps between. So when we're talking about a discrete set of data, we're talking about just basically, I like to call it as whole numbers. There's gaps between. It's not a continuous set of numbers. So we could use numbers like 1, 2, 3, 4, whole numbers. I could also set it as it's going to be 1, 1.5, 2, 2.5, 3, 3.5. The x values are fixed. There's nothing in between, no random numbers in between. So, and the probability distribution of a discrete random variable x lists the x values and the probability. So same thing here, okay, where we have the x values listed here. Okay, so an example would be 1, 2, 3. There's a whole bunch of numbers between 1 and 2 that aren't there. Okay, and then the probabilities are just listed below. So let's take a look at an example. Again, I think it's really simple. Example 1 says, how can we quickly assess baby's health at birth? Okay, in 52, Dr. Virginia Abgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. A baby's Abgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. So you're not going to get a 1.5 on any of these. It's going to be a 0, a 1, or 2. And we're going to add them all up. Abgar scores are still used today to evaluate the health of newborns, although this procedure was later named for Dr. Apgar. The acronym APGAR also represents the 5 scales: appearance, pulse, grimace, activity, and respiration. What APGAR scores are typical? To find out, researchers recorded the APGAR scores of more than 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. Random. Right there's our chance process, correct? So we're at random, and that's our chance process. So define the random variable x equals the APGAR score of a randomly selected baby 1 minute after birth. The table gives the probability distribution for x. Show, so here's what I'm asking you, all of that to show the probability distribution for x is valid. So again, here is my x values, right? Okay, 0, 1, 2, 3. And the higher the score, the healthier the baby. Okay, and then here's the probability. Okay, so there's the probability. So how can I show that this is valid? Number one, all of the probabilities are between 0 and 1, right? All the probabilities are between 0 and 1. So we would just say all of the probabilities are between 0 and 1. If any of these values was less than 0 or greater than 1, it's not valid. Okay. So the second thing, we've got to add all these up. So I'm going to add up 0.01 plus 0.006 plus 0.007 plus dot, 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 all the way up to the very last probability, which is 0.053. And when I pick up my calculator and add all those, it does equal to 1. That's something that you should do right now is pick the calculator up, add up all of these values down here, and make sure the probabilities are equal to 1. So since they do equal 1, it is a valid probability distribution. Okay, so let's move on to objective 2. Calculate probabilities involving a discrete random variable. How likely is a mother to have a healthy baby? So doctors decided that an APGAR score of 7 or higher indicates a healthy baby. What's the probability that a randomly selected baby is healthy? So randomly selected, we're looking at these 4 values. Okay, so I'm looking at a baby with a score of 7 or higher, which includes the 7. So I'm going to add up 0.099 plus 0.319 plus 0.437 plus 0.053. Okay, so again, get the calculator up, add up those probabilities. 0.437 plus 0.053, and I get a probability of 0.908, which is approximately 91% of babies are healthy. So again, why did I include the 7? Because it says a score of 7 or higher. If it said just higher than 7, I would not have included the 7 and just done the probabilities for the numbers 8, 9, and 10. Okay, and again, why is this a discrete random variable? Because notice you can't have a score of 0.5. It's either a 0, a 1, a 2, a 3. So this is a discrete probability. And again, another way that we can say this is we could say at least a score of 7. Okay, so if you see the word at least, I'm also going to include that 7. If it said a score higher than 7, then I would not include the 7. All right, let's look at objective 3. Classify a random variable as discrete or continuous. Now, continuous random variable is where I no longer have any gaps. Every single number is included. So capital X can take any value in an interval on the number line. Okay, and a lot of times this is when we are dealing with a measurement. Okay, so when we're talking about measuring something, a lot of times that is a continuous set of random variables. Okay, so if we take a look at, whoops, I forgot to do the last one. Let me look at this real quick. Get the variables up here. Here we go. Sorry. I forgot to add this slide. We need to do that. Okay. So let's add this slide with 3 variables. And all I want you to do is to tell me whether or not this is a random variable or a discrete set of data. Okay. So if we go ahead and look at, like I said, objective 3, a continuous variable a lot of times is dealing with measurement. So classify each of the following random variables as discrete or continuous. If X is equal to the foot length of a randomly selected student, foot length. So we are dealing with a measurement. So this would be a continuous random variable. Now, what if I said foot or shoe size? Sorry. What if I said shoe size? Well, shoe size is either a 1, 2, 3, 4, 1.5, 2.5, 3.5, 4.5. There's no 1.25 shoe size. So this would be continuous. If I ask for shoe size, that would be discrete. Okay. The number of pumps out of 12. So you're not going to have in use at a gas station. So you're not going to have 1.2 pumps at a gas station. So this would be discrete. Okay. And then the string tension of a randomly selected tennis racket, typically any value between 50 and 70. So any value means that this is a continuous there we go, a continuous random variable, because it could be 50.25, could be 50.11, okay, could be 70, could be 68.31. So this would be a continuous. So we need to be able to tell the difference between a discrete random variable and a continuous random variable. So you got some problems on Edulastic to do. Like I said, should be a fairly simple section. Have a good day.